Welcome back. It's our last lesson in this unit on techniques of integration. Today's learning objective is to, number one, define improper integrals, and number two, evaluate an improper integral or determine that the integral diverges. First, what's a proper integral? An integral expression is considered a proper integral if the limits and the function are bounded. Proper integrals are always well defined. The function's defined and bounded on some interval, AB, and the limits of integration are finite. What about improper integrals? Integrals are considered improper if one of two things occurs. Number one, on the interval AB, A and or B is infinity. Number two, somewhere between A and B, there's a discontinuity. So we're going to start with scenario one, if A and or B is infinity, and we'll start with looking at this function here, 1 over x squared. So the example asks us to first sketch the infinite region R that lies under the curve y equals 1 over x squared. So there's 1 over x squared above the x-axis, okay? Then shade the area to the right of the line x equals 1. So we need a line x equals 1 and some value x equals t. So we're going to shade that in. All right, now we're going to solve the integral going from 1 to t, the area under the curve from 1 to t. So first step, let's rewrite that as x to the negative 2. And then we will take the antiderivative, which is negative x to the negative 1, and evaluate from 1 to t, which would give us this, negative 1 over t minus 1, which is negative 1 over t plus 1. Now, what is this t? It's just some arbitrary number that we've said, well, the graph stops there. But that arbitrary number could just keep moving and moving and moving to the right. It could go all the way to infinity. That's what we're going to do. We're going to let it go to infinity. So we'll take the limit as t approaches negative infinity of negative 1 over t plus 1. So as the bottom here gets really, really, really big, this whole thing goes to 0. And so we just get 1. So even though this graph continues to grow and grow and grow and grow and grow and grow, the area under the curve is approaching 1. We say that this interval converges. The area under the curve is heading towards a finite number. So let's generalize or formalize this a little bit. Let's look at number one. If f is continuous on the interval from a to infinity, then what are we going to do? Well, we can't say a to infinity because infinity is not a number. So we have to change infinity. We got to give it a new name, and we'll call it b for now. And then we take the limit as b approaches infinity of the integral of the function. 2 is similar. If we're going from negative infinity to b, well, negative infinity is not a number, so we have to rename it. So we'll rename it a and then take the limit as a approaches negative infinity. Now, scenario 3 here is if f is continuous from negative infinity to infinity, then what do? Well, we're going to have to break it up because you can only have one part of the integral that's improper. And right now we have two parts of the integral that's improper. So between negative infinity and infinity, we'll put some constant c there and break it up. So negative infinity to infinity becomes negative infinity to c, and then c to infinity. And then each of these problems takes you to either scenario 1 or scenario 2. Couple helpful hints for you. Remember that evaluating an improper integral is really two problems. It's an integral problem and a limit problem. So it's best to evaluate them separately. When breaking down improper integrals, be sure each integral is improper at only one place. And that one place should either be the lower limit of integration or the upper limit of integration. So we'll start with this one. We're going from 1 to infinity of 1 over x. So first of all, we're going to rewrite this as a limit because infinity, well, that is not a number. So we'll rewrite it, renaming infinity as b, and then take the limit as b approaches infinity, okay, from 1 to b, 1 over x dx. Now we can just integrate and evaluate. So the antiderivative of 1 over x is ln, absolute value of x. So we're taking the limit as b approaches infinity of ln of x from 1 to b. So we've integrated it. Now we will evaluate it. So we've got f of b minus f of 1. Now the ln of 1 is 0, so that actually just disappears. So we're just taking the limit as b approaches infinity of ln of b, which is infinity. Okay, what does that mean? So look over at the graph here. We're talking about the area under the curve from 1 to infinity. So see how this area under the curve is just going to grow and grow and grow and grow and grow. It's infinite, which means the integral diverges. A little peek into the future here. We're going to cover this in Unit 10. If you have an integral that looks like this, like some constant to infinity, 1 over x to the p dx, that'll be convergent anytime p, the exponent down here, is greater than 1, and divergent anytime p is less than or equal to 1. Let's try another one, x e to the x dx. So the area under the curve from negative infinity to 0, that negative infinity is a problem. We can't have that there. So we need to rename it. Well, let's use t this time. So now we're finding the area under the curve from t to 0, okay, x e to the x dx, and we'll take the limit as t approaches negative infinity. Okay, now how do we take the antiderivative of x e to the x dx? Well, lucky you, we get to do integration by parts. So we'll say that u equals x, dv equals e to the x dx, which means u prime is dx, and v is e to the x. And then our formula is uv minus the integral of v du, or ultraviolet voodoo. So we have uv minus v du. Now let's go ahead and rewrite that in our limit notation so we don't forget what we're doing here. The limit as t approaches negative infinity of this whole problem. And then we'll integrate that fellow there. And so the antiderivative of e to the x is just e to the x. Now we can evaluate from t to 0. So we have f of 0 minus f of t. Now we have a 0, that goes to 0. E to the 0 is 1. And then t e to the t, what is that? Let's come over here just a second. That would be negative infinity times e to the negative infinity. Well, e to the negative infinity, that's the same as 1 over e to infinity. So really, this is what we're working with. And the bottom's going to grow a lot faster. So this goes to 0, and this also goes to 0. So that all just equals negative 1. So the limit exists, it's negative 1. Therefore, the integral converges. Okay, so now we're getting into where both of the bounds are improper. So we're going to have to break this guy up And usually an easy spot to break it is at 0. So now we're going negative infinity to 0 of 1 over 1 plus x squared, and 0 to infinity 1 over 1 plus x squared. Do you recognize this 1 over 1 plus x squared? You can't use u substitution because if u equals 1 plus x squared, you get du equals 2x dx, and that's not helpful. There's no way to factor the bottom, so we can't use partial fractions. So then we're like, what else could I do with 1 over 1 plus x squared? Well, this is a recognition thing. The antiderivative of 1 over 1 plus x squared is tan inverse x, okay? And then we'll put the limit back onto it. So the limit as a approaches negative infinity, tan inverse x from a to 0. The limit as b approaches infinity, tan inverse x from 0 to b. This one's easier if you can see tan inverse of x. So let's do like the a portion first. The limit as a approaches negative infinity of tan inverse of 0 minus tan inverse of a. That's f of b minus f of a. And then we'll add to that the limit as b approaches infinity of tan inverse of b minus tan inverse of 0. Okay, so now evaluating each of these, what's the tan inverse of 0? That's just 0. Tan inverse of a, well, that's the limit as a approaches negative infinity. That is negative pi over 2. And then as b approaches infinity, so tan inverse of b, as we're going to infinity, that's pi over 2. And tan inverse of 0 is just 0. So the answer to this one is pi. So we have a limit that exists. The integral converges. This is the graph of it. So the area under the curve here, even off to infinity in both directions, is approaching pi. So we've worked with functions that maybe go off into infinity on the left or the right. But what happens if we've got this interval AB and somewhere between A and B, we have a discontinuity? So we're going to work with this function here, 1 over the square root of x minus 2, between 0 and 5. So first of all, so we can see what we're dealing with here, let's graph it. And why would 1 over the square root of x minus 2 be considered improper? Well, it's because of this vertical asymptote here at 2. So if 2 is a problem, we can't have it as one of our bounds. So what we have to do is we'll rename 2 as t, and then take the limit as t approaches 2 from the right. The graph doesn't even exist to the left. Now let's solve the integral. We're going to have to use u substitution on this one. So u equals x minus 2. U prime du equals dx. So now we're integrating 1 over the square root of u, which you can rewrite as u to the negative 1/2. Add 1, divide by it. We now have the limit as t approaches 2 from the right of 2 times x minus 2 to the 1/2 evaluated from t to 5. So we'll plug in 5. We've got f of 5 minus f of t. Let's see, 5 minus 2, that's just 3. And then now we can do a direct substitution of 2 in for t. And 2 minus 2 is 0. So the final answer is just 2 root 3. So again, let's generalize or formalize this. If we have a continuous function on the interval AB, notice this is an open bracket, and we have a discontinuity at B, then we can't use B as one of our bounds because there's a discontinuity there. So we'll have to rename B with a different letter like C, and then take the limit as c approaches b from the left. For scenario 2, now we have a discontinuity on the lower bound at a. Then we can't use a as our lower bound, so we'll have to give it a new name, like c, and then take the limit as c approaches a from the right, and then solve from there. Now, if there's some kind of discontinuity in the middle of AB, let's say there's a discontinuity at C, then just like we did before when we were going from negative infinity to infinity, we just have to break it where the discontinuity is. So we go A to C and then C to B, and then you'll have like back to scenario 1, back to scenario 2. So let's try this one. We're going from 0 to 1, ln of x dx. Now, why is that a problem? Well, if you graph it, you can see that ln of 0 is undefined, so we cannot use 0 as one of our bounds. So we'll have to rename that as something else. We can call it a, and then we'll take the limit as a approaches 0 from the right, ln x dx. All right, how do you take the antiderivative of the natural log? That would be integration by parts. So u equals ln x, dv equals dx, which means u prime is 1 over x dx, and v equals x. And then we do our ultraviolet voodoo. Now we have the limit as a approaches 0 from the right, x ln x minus the antiderivative from a to 1 of, this is just basically a 1 here, isn't it? 1 dx. Okay, so here's our final antiderivative, and we'll evaluate that from a to 1. So here's f of 1, because ln of 1 is 0, and then if you plug in a 1 for x, then you just get negative 1 here, minus f of a. And then we can take the limit as a approaches 0 from the right, you get negative 1 minus plus 0, which is just negative 1. So we're looking at the area here. So that makes sense that it would be negative 1. What about 0 to 3, 1 over x minus 1? Well, if you graph it, you can see where the problem is. It's at 1, which makes sense because 1 makes the bottom of the fraction 0. So that means we've got to break this integral at the problem area. So we'll go 0 to 1, and then 1 to 3, and now we need to make a limit problem out of each of these. So the first one, the limit as b approaches 1 from the left, 0 to b, and then the limit as a approaches 1 from the right, a to 3. And then the antiderivative of 1 over x minus 1, this looks kind of crazy, doesn't it? Is the ln of x minus 1 from 0 to b, and then the limit of x minus 1 from a to 3. Oh golly, then we have to evaluate this. So here we've got f of b minus f of 0, and then f of 3 minus f of a. So let's just evaluate this one step at a time here. This first little part, we've got the limit as b approaches 1 from the left of b minus 1. Well, as 1 approaches b from the left, you're ending up that it's going to negative infinity. That's going woo down here. Well, you can stop when any part of this diverges. So the rest of this, we don't even care about. The limit doesn't exist, it diverges. So that's that, your last lesson in integration. Thanks so much for hanging in there for a long unit with me. You guys are awesome. And hey, I'll see you in the next unit.